Hello, my name is Luke Rowen, and I will be presenting my research on the hydrodynamic purposes of the Chondrocladia Lyra skeletal structure. The Chondrocladia Lyra, or the harp sponge, is a species of carnivorous sponge discovered off the coast of California at depths of approximately 4,000 meters. The basic structure, termed a vein, is composed of 1 to 6 veins radiating from the center in an equiangular fashion, giving it a harp-like appearance. Every vein is composed of a horizontal stolon, as seen right here, which supports equidistant cylindrical branches with a swollen ball on top of each branch. Each vertical branch becomes smaller in height as it goes farther from the center. While there has been study into the mechanical properties of the Chondrocladia Lyra skeletal structure, study of the hydrodynamics of the structure has remained relatively unexplored, leaving the question of how fluid dynamics has influenced the morphology and physiology of Chondrocladia Lyra. This study employs computational fluid dynamics using SOLIDWORKS to study how the presence of space between vertical branches and the standard structure of the vertical branches may affect fluid flow, thereby providing insight into how the Chondrocladia Lyra may have evolved as a result of its environmental conditions. This study has implications in the field of underwater engineering under a form of biomimicry, as well as opening the path towards new numerical methods in the intersection of fluid dynamics, computational biology, and environmental physiology. My objectives for this project were to create theoretical disentangled morphologies for the Chondrocladia Lyra, which consist of a solid rectangular, solid slant, non-solid rectangular, and non-solid slant, where I disentangle the features I had referenced in my background, and then to run fluid simulations on the morphologies, and then from that compare values such as velocity, turbulence, and coefficient of drag to gain insight into how their structures may be affecting the fluid flow around them. This study originally planned to make use of a lattice-Boltzmann simulation coded on a Python to model fluid flow. However, time constraints proved to render this infeasible. Instead, I used SOLIDWORKS as an apparatus for modeling fluid flow. Given the depth and location of the Chondrocladia Lyra, I was able to obtain information for the velocity distribution, temperature, and pressure of its natural habitat, which is crucial for modeling fluid flow. In terms of velocity distribution, the velocity ranges from 0 centimeters per second to 12 centimeters per second. It has an ambient temperature of around 1 degree Celsius, and the pressure is around 337 atmospheres. I employed 4 theoretical morphologies: solid rectangular, solid slant, non-solid slant, and non-solid rectangular, as pictured in the slide. This allows for the isolation of features of interest. Using Onshape, the 4 morphologies were created and then transferred to SOLIDWORKS for testing. Simulations were run at varying initial velocities, reflecting the reference velocity distribution, and values such as average velocity, drag force, turbulence dissipation were collected. From drag force, the coefficient of drag was calculated for the morphologies. As of now, data has only been collected for an initial velocity of 4 centimeters per second. Looking at the statistical steady state of the coefficient of drag, the solid slant had a value of 1.26, solid rectangular had a value of 1.131, the non-solid slant had a value of 0.348, and the non-solid rectangular had a value of 0.406. While little change can be seen going between rectangular and slant, there is a significant drop in the coefficient of drag going from solid to non-solid, almost 4 times less. This is likely due to the decreased surface area, thus the presence of space between the between the vertical branches, reducing the stress experienced by the skeletal structure. In terms of velocity, while the average velocity is relatively the same across the 4 morphologies, approximately 3.9 centimeters per second, there is a vastly different velocity distribution in the wake of the sponge. For the solid morphologies, the velocity goes from 4.7 centimeters per second to 1.5 centimeters per second, where in the non-solid morphologies, the velocity goes from 4.1 centimeters per second to 3.7 centimeters per second. I hypothesize this is to help with distribution of sperm. For this species of sponge, sperm is produced in the terminal balls at the end of the vertical branches and then disseminated into water to reproduce with other Chondrocladia lyras. More research is needed in order to test this. Specifically, I'd like to evaluate the velocity at a probe located in the wake of the sponge. In terms of the difference between the slant and rectangular morphologies, I have not found any meaningful difference in the given data set. For future work, I would like to investigate entropy, vorticity, and helicity, as well as conduct simulations at higher velocity. I believe these changes could provide insight into how the slanted structure might influence fluid flow. Specifically, I think the presence of the slanted vertical branches might cause the formation of vertical structures. Thank you for listening.